could it be the substance that we bathe, drink, brush our teeth with, and swim in holds a new secret, a controllable inertial mass property? And by extension, could it be a working fluid for the long-awaited deep space rocketless propulsion system? We've talked about warp drives, inertial propulsion, and now we're going to be talking about an accidental discovery that Wayne made in 2022 with water, and how this amazing everyday substance may be a great candidate to achieve inertial mass control, making interplanetary travel feasible with a concept he calls the variable inertial mass impulse engine, or VIMI.
VIMI, that's right.
Welcome back, sir. It's been a while. It has been quite a while. Do you have a screen share for me, or?
Yeah, I've been busy with moving and life and stuff. I guess you can hear me okay?
Mm-hmm.
I'm gonna try, I hope this all works. Oh, display okay.
That's awesome, dude. You just get the slideshow award for that. I'm serious. That's like MacGyver. That's the MacGyver PowerPoint. Sweet. I'm not teasing you. I think that is the coolest thing ever.
That's innovation right there.
Yeah, go for it, dude. Go for it. I can see it fine.
All right. So here we go. Water. So fourth phase and its anti-gravitational property, at least that's how it appears. I know there's a bit of, there doesn't seem to be much unity around the idea of anti-gravity, or what I mean is, inertial mass being synonymous with gravity. So it could be that there's like a mass altering or inertial mass altering phenomenon, and then that affects gravity due to the relationship mass times mass. So anyway, a little bit about my background, how I kind of arrived at here, and the process of this development. I'll touch on a few things depending on how, I don't know how much time I have. I don't want to, try to be respectful of people's attention span and time. Tim? I guess he stepped away. So metals and magnets, the seawater, other fluids, having trouble with believing the data that I'm seeing and feeling like I'm going crazy. And then just doing more experiments, collecting more data to confirm this discovery, which seems to be pretty convincing to me at this point. Now, water phases, transitions, molecular structures, and I'm not going crazy after all. And some ideas on how to modify this effect and apply it to some sort of inertial mass propulsion. So about 30 years ago, I was quite inspired by a movie you've probably all heard of, Back to the Future 2, and the hoverboards really captivated me. I was quite interested in science and electronics as well. I developed the hypothesis that gravity could be countered with magnetism. And in 7th grade, I made a crude electromagnet for a science project and hung it on a balance, like a fishing scale with a switch and a battery. And needless to say, my results were inconclusive, and the teacher wasn't that impressed that I would even tackle such a topic. 20 years later, after graduating from a mechanical engineering tech program, I was set on with gravity research again. And so I started looking online, and I came across a couple of books that kind of got me started. One was called Antigravity, the Alto of the Truth by Richard P. Crandall, and Antigravity Propulsion by Dr. Paul LaViolette. So in Richard's book, I learned he had quite an elaborate theory about, basically it was something like a Robert Forward's drive. I won't really go into all the detail of the theory right here because it's quite deep, but basically it's kind of like where I got the idea of gravitomagnetism and how this is responsible for so many of these gravitational effects. So that book got me thinking about T.T. Brown, Antigravity, Henry Wallace, Bob Lazar, Pod Klitnoff, and how all these concepts kind of tie together. So I was experimenting with putting like cone-shaped metals like aluminum in magnetic fields to look for gravitomagnetically induced nuclear mass dipole phenomena to produce this type of gravity-based propulsion, which he theorized. So I experimented with that pretty crudely, and on and off, I tinkered with some of the high voltage type experiments with T.T. Brown and stuff like T.T. Brown concepts. Years later, I came across some stuff about Fred Alzafon and gravity control through the Aaron Murakami's Energy Science Tech Conference, which used to be Bedini and Lindemann and those guys. So after studying Alzafon and the stuff Crandall was talking about in his theory, and I started to, because they arrived at this this conclusion separately, that something about polarizing atomic nuclei was the key, or the key idea for gravity control. So that's kind of how I got down that path of the dynamic nuclear orientation, dynamic nuclear polarization concepts, which got me experimenting with the Alzafon experiment a couple years ago. And that's how Mark and I crossed paths, is through that experiment, because we were both doing it. We're trying to. So I started like recently playing around with, because I'm trying to tap into this gravitomagnetism, and I saw the connection with magnets and the concepts from NMR, nuclear magnetic resonance, and from what I read from Crandall and Alzafon. So I was thinking about, well, what would happen if you put some of these metals in magnetic fields? Like, would they change their weight? Would they, I was looking for something, and I actually wasn't disappointed, especially when I got an analytical balance last fall, and I've been doing a lot of videos and stuff with this balance, a lot of experiments. But it's really showed me, kind of like opened up a number of things for me that probably would have been unnoticed before, because they are small effects, like tens of milligrams. So this little chart here shows, like with copper, seeing some weight increase. So I was doing a lot of work with that, and to this day, I don't really have like a conclusive explanation, but I have some theories. So one day I was at the beach, and I'm like, you know what, maybe I should try seawater, right? Put some seawater in a magnetic field and see what happens. Hang it like this with a magnet and some seawater in there, hang it on the balance. So after doing this for some time, sure enough, I saw some weight loss. I saw some changes. And so I'm like, oh, wow, this works. So like an early experiment was having a little jar with seawater in it and some magnets attached to it, and I just hang it on the balance. And then over time, I'd see, 10 milligrams, 20 milligrams drop. And so this picture here is an example of that, an early experiment with a paper cup, magnets, seawater. And then even putting it in someone mentioned, oh, it's probably evaporation. I think that was Mark. I'm like, yeah, it probably is evaporation. Let's put it in a sealed container. So I put it in a sealed container, big magnet, seawater on this triple beam balance with the lid on. And lo and behold, I left it overnight and it dropped, as you can see there in that picture. It dropped noticeably. And I did that a number of times and I keep seeing this result. So I thought, well, this must be what's going on. So I started collecting more data with these different little experiments I did, and I graph it. Here's a nice, nice chart showing there's some clear effect going on here. Drop of, 50 milligrams in that neighborhood. And I did another test where I would, I had 2 cups, one with just magnets and one with magnets and the seawater in it. So the one with just magnets is these red bars here. You see how it's pretty steady. Then the one with the seawater and the magnets, see this decline. So I thought, wow, that's great. This is like, but then doing more work with controls. So I've seen these, pretty predictable drops in weight when I graph up the data. And then I tried, I really should do a control. So let's just take one jar of just water, pour it in a little, pour it in there and weigh it and do the same thing. And then I found, okay, so the control jar was actually losing weight, the one with no magnetic field. And then the one with the magnetic field was not really performing. And I thought, oh, that's interesting. Now I'm really going crazy. So what I'm learning about science is when you get a negative result, it's another lesson, wrapped in gift wrap paper. There's something deeper going on. So I did more experiments. I tried glass sheets in water, and I saw weight loss with these kinds of things. I didn't with this. This was like a sealed jar. These were other glass jars. And I tried a mechanical balance, putting containers with salt water on it and seeing some results with that too. I started to realize it was about probably like surface area. So I started getting into, I thought about capillary tubes, but that's a bit later. So the question of evaporation was still kind of haunting me, and I hadn't convinced anybody really in our chat or anything. So I decided, well, let's take the two, let's compare jars with lids off and jars with lids on, so that let's see if evaporation really is a factor here. So what I do is, have 2 different jars. Lids off and 2 with lids on. One would be salt water, one would be salt water. So the results of that was this data here. Basically, the green line is showing the jar with the salt water and the lid on actually lost the most weight. The ones with the lid on to prevent evaporation lost the least amount of weight. Well, that was interesting. And I tried different solutions. I tried like copper sulfate, calcium chloride, just some different chemicals from a chemistry set. And here's the list of the ones I tried. Some big long names like potassium hexacyanoferrate. And that one actually performed the best out of all these graphs. The orange line here was the potassium compound. This was the sugar water, and this was the copper sulfate solution. If you notice, it barely moved at all. So what I do with these experiments is I just kind of like every period of time I would weigh each one and write down the weight, check the with the calibration weight as well. Make sure it's telling me the truth. So I just kept working with this this stuff. Like I mentioned before, I thought about capillary tubes because I was starting to see that it had something to do with the container and the fluid in the container and that the interaction with that over time. So I got some capillary tubes. Here's the results from distilled water, basically a 70 milligram drop over, let's see, 12 to 8. How many hours is that? 8 hours. So you notice the sudden drop in the beginning. And then in this graph here, this shows the same kind of trend. These were bigger capillary tubes, like 1.5 millimeters. And these are the small ones, which are like 0.3 millimeters. And here's just some pictures, some examples of what that looked like. So I had a pop bottle, which I sealed with very tightly. I also put some dielectric grease on them to make sure there's no evaporation at all. So in each case here, they all showed weight loss trends over time. I tried shaking them, and the shaking would not change the reading on the balance. Or neither would orientation. So like laying it horizontally or vertically. Here's a graph of the saltwater one, which was one of my earlier experiments. You see that exponential curve. And this is like 4 hours, 8 hours, 12 hours, 16 hours. Before and after, 100 milligrams loss in weight. Looks and feels great. So I got into Pepto-Bismol because I wanted to find something with bismuth already in solution. I thought about bismuth bromide because it's so very soluble, but Pepto-Bismol is a lot more easy to buy, and it does have bismuth atoms in it. Bismuth it's a big atom with lots of nuclear spin and mass. And I thought, because I think this has something to do with gravitomagnetism, I thought that would be a good candidate. So I tried it with the capillary tubes, and here's the results with that. There was a quick initial drop of 100 milligrams once the Pepto-Bismol interacted with glass tubes. And so here there's another, over about 12 hours, there's another drop of 50 milligrams, and then it starts to level off, plateau. And this is an extension of that graph. Just as time goes on, see how it stabilizes there. Just more pictures of that setup. So there's the pop bottle. In there was a test tube, which I put the Pepto-Bismol in. I sealed it up with this cap, silicone dielectric grease. And then what I did was I weighed the whole thing like that. And then I poured it out so it got on the tubes. And then I weighed it again. And you see the difference there was quite large, like 100 milligrams. And I tried another one with a different digital balance. So in here was the bigger tubes, 560 glass tubes, 1.5 mils diameter. So this is a sealed, like a food container. So it was like a rubbery plastic membrane here. And what I noticed was most of the weight loss occurred in the first couple hours or so, and then it just stopped. Didn't change at all after a day. And then I was thinking about, okay, because this has something to do with surface area, and contact with surface area. So I thought about stranded wire. I had this car audio speaker cable which has like all these like strands of wire on it. So I tried it, didn't do anything. I thought, well, that's interesting. And so I thought about what might be the reason why, and did a little research and found out these wires are actually tin coated. They're tin coated copper to prevent oxidation. And so I realized this probably has to do with, there has to be like the oxygen atoms have to be attracted to the surface, and they're not very attracted to tin, from what I read there. I tried aluminum heat sinks because there's lots of surface area. So what I did in this experiment was I weighed this container here, water at the bottom, and this heat sink on top. And so it was, as far as I could tell, balanced. And then what I did was just immerse it in the water, put the cap on, and shortly after, there was a noticeable drop. And that was about 100 to 200 milligram range. And I just tried other types of experiments with these on my other balance. And there was always a weight loss, and it happened quickly, and then it plateaued. So thankfully, Jeremiah had a go at this, and he tried a few different experiments. Unfortunately, he had some problems with his video processing, so I wasn't able to get all the data from that, but I got enough to show a general trend. He saw weight loss as well, and it just kept going and going. And this is milligrams here, tens of milligrams. So he did a really good, really interesting experiment. This is like the little container. These are the capillary tubes, the small ones. So he hung them on a thread in there, and there's a little bit of water at the bottom. And he noticed that after he poured the water, and this is dead water too, like this is deionized water that was sitting there for months, like under his bench. And he noticed some few milligrams of weight loss just by the water being in contact with the surface of the container. And then he took a laser pointer and burned the thread in there so that these tubes fall into the water. So he didn't ever open the lid. And then the water was wicked up the tubes, and the trend of weight loss just continued on for quite a bit longer. And he also did this experiment with the pop bottle and the tubes. I think he reported, 70 milligrams after 34 hours. And it was like 10% Pepto-Bismol and 90% bottled water. And he did this other test too with these, he had these little bags he could seal, like, I guess for storing food or whatever, like freezy, like freezy pops. But anyways, it's totally sealed. So he put Pepto-Bismol and water in another one, and those just kept losing weight, like tens of milligrams. So so the thing about water is everyone is a water expert because everyone thinks they know everything about water. We know that it's a solid liquid gas. Water is everywhere, and we drink it, falls from the sky, boils at 100 degrees, freezes at 0 or 212 or 32 for those of you who like Fahrenheit. We use it for cleaning, we play in it, drink it. So we know water quite well, don't we? But less people know it expands when freezing, forms hydrogen bonds within itself. It's composed of H2O, deuterium, tritium. It's called the universal solvent. It absorbs large amounts of energy during physical phase changes. Molecules rotate, bend, vibrate, and twist. And it's decomposed into hydrogen and oxygen. Fewer people know that water has many ice phases. In fact, I didn't know this until recently, but there's actually up to 19 different types of ice. And so this is temperature here and pressure. So the greater the temperature and pressure, you see these different zones here represent the different types of or phases of ice. And then there's something called super ionic ice, which is believed to be a big part of the gas giant, the cores of the gas giant planets. And some scientists believe it is a new phase of matter. It's either in addition to water's already cluttered array of avatars or something even stranger because its water molecules break apart, said the physicist Livia Bove. It's really a new state of matter, she says, which is rather spectacular. Millo's team found their super pressurized ice melted at around 4,700 degrees Celsius, about as expected for super ionic ice, and that it did conduct electricity thanks to the movement of charged protons. So it's kind of like an amazing conductor, but instead of moving electrons through, like with ordinary conductors, it moves protons, which are the hydrogen atoms. That's from Quanta magazine. So I'm thinking that maybe this weight loss effect might be related to phase changes of matter and a different phase of water. So yeah, it turns out this scientist, Dr. Gerald Pollack, and his team, they have discovered what they call the fourth phase of water. And so I'm so glad I came across this video recently, because it really confirmed a lot of things, that maybe there is this other behavior just ordinary solid, liquid, and gas. So he described it as being jelly-like, this fourth phase, in between solid and liquid. And it excludes all particles, impurities, and for that reason, they've called it the exclusion zone, or easy water for short. And so when easy water forms, they found an electric field spans across it. And it can act a distinct molecular formation resembling a grid of hexagons. I have a diagram. And it forms on hydrophilic surfaces like glass. And I have found in some of my experiments, it seems to be related to heat. I won't play these videos right here because it's kind of awkward, but it's on YouTube here, the fourth phase of water, Dr. Gerald Pollack at TEDx. And what is the fourth phase of water? So I recommend watching those if you haven't, or if you want to get more understanding on this. So this diagram here, I don't know if you'll be able to see it, but basically, this is from the videos I watched. This is my hand-drawn diagram. So this is the surface here, like say glass or other surfaces, hydrophilic surfaces, and these easy layers form over time, and they form in sort of like a honeycomb pattern with your oxygen atoms and your hydrogen atoms, and they overlap. And he calls it H3O2. And this is an example of, so here's the surface. And you can see the positive charges and the negative charges here. So there's a polarization that happens across this easy zone. And shining light on it or warming it apparently expands it. And this is like particulate matter, impurities, salts, and that sort of thing. It gets expelled from this easy zone. But I was also thinking about glass, right? Glass is interesting too. So I thought maybe could the water be forming a glass-like phase? So this one scientist says the deepest and most interesting unsolved problem in solid state theory is probably so when things glassify, molecules slowly settle into tightly packed, dense formations. And I think it may have something to do with Pollak's exclusion zone water, but also this mass loss property, which suggests that there could be phase transitions involving changes in inertial mass in other substances too. Crystal formation, liquid formation, and glass formation. So it's like a liquid, but it doesn't have the crystallization. Got me thinking about clouds. I started to see clouds and fog in a new way. That maybe these droplets are actually somewhat weightless, like they're not actually being pulled to the ground like every other particle would. So I found out that cloud droplets are on average 20 micrometers in diameter, and the raindrop is like 2,000 micrometers. So the average raindrop, that's when they fall. So there's actually been a lot of studies done about droplets and their size and how long they stay suspended in the air, and whether they fall or not. And it depends on their diameter. So what I'm thinking is that this easy water forms on these aerosol particles in the atmosphere. And it's a very small, like we're talking, 10, 20 micrometers in that range. And it's not actually it doesn't actually couple with the Earth's gravity. It's almost massless. It's kind of what I'm proposing. So I think it might be a fourth phase of water, highly ordered dense phase of H3O2. And I can provide the slideshow by email or whatever later, so you guys can look at it later. Or I can forward research. So I'm thinking basically these droplets will never be pulled to the ground by gravity. This is the reason why clouds float in the air. They don't. But as more molecules coalesce with these droplets, of course, they start to gain mass, so they have a different mass property. But more work needs to be done with that, because that's just my hypothesis. And I was thinking about how it applies to, nature and trees and plants, and how water wicks up these very high, very tall trees. And, water tends to feel heavy, right? When you pick up a bucket of water or whatever, it's pretty weighty. And yet it just keeps rising up the stalk of a tree. These are local trees where I live, by the way, they're huge. And these actually have little capillary tubes, basically little capillary tubes inside of them. And I see that as like brilliant engineering, actually. The more I study this stuff, it's like, it's evidence to me that things are designed and created rather than happen by chance. But so what I know and what you guys know now today. So now we're all water experts, right? So as water in distilled or solution forms is poured into a hydrophilic container such as glass or some plastics and interacts with these surfaces, the weight drops exponentially. As this easy water layer or skin forms over time, this fourth phase is losing. Now this is where it gets interesting. It's either losing coupling to Earth gravity, but not inertial mass, or inertial mass and therefore gravitational force, which is the equivalence principle. So A makes gravity reduction or anti-gravity possible, but useless for propulsion. B is not anti-gravity, but inertia control, and therefore useful for propulsion. So is this a natural kind of coherent matter? A natural nuclear orientation, polarization of nuclear gravitomagnetism? Does the Earth's ether flow pass more freely through this coherent state, thereby causing less resistance? Is there less vacuum fluctuations in easy zone water and perhaps many other substances in a glassy state? All this remains to be understood. Furthermore, and by extension, during the crystallization of water during freezing, it likely is losing weight. Although this experiment is a little more difficult to carry out because of condensation problems, but I did actually take a stab at this. And what I found was, so this is weighing it as an ice cube, and this is weighing it hours later after it's melted. And so you see there is a slight change here. I measured about 25 milligrams. And that's a Ziploc bag and a cup to isolate, so that like thermally isolate. I did a similar experiment later on. Again, melting ice cubes, a styrofoam cup, freezer bag or Ziploc bag, sorry. So this was the progression of the weight over time. That's 8.3243. So about a 40 milligram loss after melting. So when it had warmed up to room temperature. So now I was racking my brain on how to perhaps control this phenomena, because that would be the most useful aspect of it. And I came up with some positive results, although not very useful at this point. But one of them, I just took a pickle jar out of my fridge and weighed it as it was fresh out of the fridge, 10 degrees Celsius, and weighed 841.84 grams. And then as it warmed up to 21 degrees Celsius, which is like room temperature, 841.62 grams. And then I warmed it up some more on the stove, and 841.49 at 34 degrees Celsius. So you see the progression of loss of weight here, and that's about 340 milligrams, right? And then I tried plain water. I used the same jar, so it's not great value anymore. Sorry about that. But, so I did the same thing here, well, similar. I started out warm. So that says 45 degrees Celsius on the surface, weighs 1,022 grams, 1,022.10 grams. And then it cooled down to room temperature, 19 degrees, and it weighed 1,021.95. And then I put it in the freezer Celsius on the surface, and then weighed 1,022.08. And then I warmed it up again at 1,020.94. That says 38 degrees Celsius. Here to here, it's predict, but here's what I think is going on. So this is weight, and this is time and temperature. So if I start out with it being hot or warm, and I freshly pour the water into the jar, it's going to have its usual drop in weight as it interacts with the surfaces of the container. But because it's starting out warm, it's going to, as we've seen, it's going to weigh a little bit less. So as it cools down, the weight is going to slightly increase. So it's going to sort of cancel out is what I'm getting at. So that's why there wasn't like a stark result in that experiment. So to do this, it's best to like let the water settle in the jar for say a day, and then heat it up or cool it down, because that way you can see more clearly the effects of temperature, because it does have this progression just from the interaction with the surfaces. So another experiment I did, I put this one on my YouTube channel. So that's a light bulb in there, and sealed lid. I sealed it with hot glue so to prevent evaporation as best as I could. So what I found was the light bulb would warm up the water, like as you can see here, from 18 to 40 degrees, and then cool down 27 down to like room temperature. So you'd see a trend of, as it warms up, it goes from 585.91 to 585.84. And then as it cools down, it increases slightly back up to 9.1, and back up a little more to 9.4. That's my video clip there, but I won't play it here. So concept I remember from reading one of James Woodward's patents, which I thought was pretty interesting. 6098924, but he describes a schematic of got a positive mass, negative mass, positive mass. So when you cycle between this mass being slightly more than this one, and then you expand the transducer, and vice versa. When you contract it and this mass is slightly less and this mass is slightly more, what you end up with is a net motion going this way. But he talked about using piezoelectric actuators, and I don't know where they're at with that at this day, but this is from an older patent. So this is basic like high school physics. So I don't know. Guys probably don't need to see this, but I just find this is really interesting because this is, even with just a very small amount of thrust, but applied for a very long period of time, you can actually attain very large distances in space. So, for example, a small acceleration of 1/100th of a g, which is like 1/100th of the Earth's gravity, you could get to the moon in 17 hours. That's like accelerating to halfway, and then you turn your spaceship around and you decelerate and you reach the moon. At that rate of acceleration, you get there in 17 hours. And after a week, you could attain 22 million or 22 million miles, 38 million kilometers. And after 2 weeks, over 145 million kilometers, which gets you past Mars or Venus. So the key is just to keep applying this small amount of thrust over a long period of time. At least for, unless we can get like to the point of a very high amount of acceleration in a propulsion system. So what I came up with is this I call variable inertial mass impulse engine. So basically the mass of water is cycled between high and low, denoted by the big M and small m. And some of my experiments have shown that higher thermal energy reduces the weight. And because I believe weight and inertia is related, and vice versa, therefore should reduce or increase inertial mass. And it appears that this can be cycled. So the cycle is reminiscent of the Stirling engine or heat pumps, like different thermodynamic states. So there'd be no need for propellant, rocket fuel, because the concentration of dissipation of inertial mass achieves the same purpose without the loss of matter. So I see matter and mass as being different. Matter, the number of, marbles in a jar, but the mass of those marbles can change. So I just see it's, hopefully that's simple enough to understand, but so basically these, you'd have two containers, say of water, and you'd have an actuator between them. And this actuator would extend and contract. And it would do so in tandem with these water tanks being cycled between hot and cold, or the surfaces. So you'd have an alternation of inertial mass, which would produce a net thrust downwards. And so for deep space propulsion, nuclear energy might be a good, well-trusted solar system, the use of the sun, solar energy, that sort of thing. Very, very conventional methods to produce this, the heat energy required to alter the inertial mass of the water. So I will, with that, I'll end the presentation.
Okay. Wayne, that is amazing. Lots of details, and you get an award for that PowerPoint. So you get the MacGyver award for the PowerPoint. Okay, let me do this. So we stopped your sharing. Let's go into Q&A session. And I should apologize to you guys. I'm kind of like, I don't want the background noise. So this room that I'm in is like, I don't know, like 90 degrees. So I'm like bright red, sweating and all that. Ugh. So again, option Y on Mac or Alt Y on Windows. I don't have a Darth Vader cup. I got my beat up coffee cup.
You should get one of these.
The Darth Vader cup.
Maybe the boss.
I'm watching that new series, the Obi-Wan series. I just watched that.
Yeah, I'm watching that too. Yeah.
Isn't that weird? Isn't that kind of sad that we're like adults and here we are on Disney Plus? I'm like kicking the kid off it. Get off my Disney Plus. Watching Star Wars.
Well, it's hard to let go. It's hard to let go when you're an 80s or 90s kid, I mean, that's kind of like
it is.
Hard to let
Yeah.
go. Especially because nothing good ever comes after the 80s or 90s.
That is true.
That's kind of the general.
It ended with grunge music, man. That was it. Grunge music, and then went straight from that to Kid Rock, and it was all over. So
yeah.
Yeah. Okay. So Mr. Mark Sokol has his hand up. Let's go to Mark.
Yes.
Yes, great job.
Hold on. Yeah. Sorry, I put this on gallery view. Everybody, let's give Mr. Wayne Ojala a giant hand.
That was amazing, Wayne.
Thank you.
I'm a little sorry that I couldn't get to see the actual presentation. We had to do it like that.